Hello, my name is Junhyeok Lee, and this is a long version introduction video of the new wave. New wave is a diffusion probabilistic model for neural audio upsampling. This work is done by Junhyeok Lee and Seungu from MindLab. This is our presentation's content: introduction, new wave, experiments, results, and discussions. From the beginning, while most of audio deep learning researches are focused on 16 kHz sampling rate, there are some demands for high sampling rate text-to-speech. Thus, we started this research to supply high sampling rate 48 kHz TTS without training new TTS model. First, we tried to apply previous researches for 48 kHz upsampling. We found that there are Spectral-alias-like Artifacts or coarse. Similar to linear interpolation Spectral-alias, UNet and mu-GAN spectrograms were almost symmetric with respect to the red line, which is the Nyquist frequency of the downsample signal. So, we tried other approach and model to avoid this artifact. Diffusion Probabilistic Model is a trending generative model which achieves high fidelity for a variety of tasks. Denoising diffusion probabilistic model defines these models on Markov chain with T diffusion steps. For our target data Y0, from right to left, latent variables are defined by adding Gaussian noise, which processes are called forward pass. On the other hand, from sample of Gaussian normal distribution Yt from right to left, the model estimates added noise to denoise latent variables. This process is called reverse process or sampling. For more details, for fixed max diffusion step T and predefined constant noise schedule beta, forward pass is defined by adding Gaussian noise gradually from target data Y0. Total forward passes probability is defined by cumulative multiplication of each diffusion step, and each diffusion step's probability is defined as Gaussian distribution. Since sum of Gaussian is also Gaussian, latent variable at step T could be defined as below. Reverse pass is the reverse of the forward pass. During the reverse pass, diffusion models estimate added noise and denoising it. Total reverse passes probability is also defined as cumulative multiplication of each reverse pass, and each pass is defined as Gaussian distribution with model estimate mean mu and deviation sigma. Diffusion probabilistic models fix deviation and handcrafted one, while mean is estimated by model. Since these denoising diffusion probabilistic models are complex and novel, we recommend to read this paper. In addition, there are two works which apply diffusion models to neural vocoder tasks. Both are conditioned diffusion model which condition on mass spectrogram to generate low audio. Since neural vocoder and upsampling are similar tasks, since both tasks generate high resolution samples from low or missing feature, like mal or downsample signal, we adopt both work for our upsampling task. This way applied bi-dilation convolution without upward downsampling, which resembles non-autoregressive wavenet, while wavegrad is more similar to UNet. Since our model's architecture is more similar with diffwave, our training and sampling algorithms are more similar with wavegrad. Now, let's introduce our model, new wave. Our contributions are as following. New wave is the first generative model, which upsample waveforms of sampling rate 48 kHz from 16 or 24 kHz without 8-bit neural quantization. New wave is the first diffusion-based model for audio upsampling. New wave outperforms previous models, including GAN-based model with smaller model capacity. This is the architecture of new wave. New wave model estimates added noise from 3 input, noise signal, current added noise level, and downsample signal. Red boxes are main changes from original diffwave architecture. Based on diffwave's bi-dilation convolution architecture, we added waveguard's continuous noise level condition, while diffwave condition on integer diffusion step. In addition, we'll replace mere spectrogram input of diffwave to linear interpolated downsample signal. During several modifications, we found that downsample signal need more receptive field than noisy one for better quality. Thus, we applied bidirectional convolution as main 1 as 2. Also, we found that several hyperparameters such as linear scale of noise level affect output quality too. Please refer to our paper for more details. We modify algorithm from wavegraphs continuous noise level training. We adjust loss and noise schedules. We discovered that loss scale between large and small noise level are quite different as 10 times. Thus, we replace error loss to log error loss. In addition, for flexible different noise level inference, noise schedule during training should cover more large noise level range. We extend mean and max noise level to cover more range. Noise schedule during inference, we could sample high resolution audio with just 8 iterations. Please refer our paper for more details too. During experiment, we train our model with famous 48 kHz multi-speaker dataset VCTK. We test our model with single speaker setup and multi-speaker setup. We test our model with 2 upsampling ratio twice and triple. During downsampling, we apply short-time Fourier transform and gyro fields to high frequencies for in-phase downsampling. We compare our model with unit-like model and MuGAN. There are number of parameters as table number 1. Our model has smallest number of parameters. Quality of upsampled signal is measured by signal-to-noise ratio, log-spectral distance, and human-tested ABX accuracy. For the result, our model can naturally reconstruct high-frequency elements than other models and without Spectral-alias-like artifacts. Also, Neural outperforms other models with smallest number of parameters. During measurement, while SNR could not measure high-frequency elements enough, we mainly select model with LSD validation. With continuous noise level training, Neural model could upsample audio with 8 iterations. We found that last step's beta should be large enough for better perceptual quality. In discussion, while our model outperforms and naturally reconstructs high frequencies, it cannot generate harmonics of vowels as well as sibilants and fricatives. In addition, output contains slight high-frequency noise. For future work, firstly, we need to optimize hyperparameters. Since diffusion models have lots of hyperparameters such as noise schedule, max diffusion step encoding, and etc., we believe that we could build better models with optimizing them. For now, research are based on our in-phase downsampling. We need to train and test models with normal downsampling methods too. Since our models take interpolated downsample signal, Neural could upsample audio from various sampling rates, so we need more experiments for this. Lastly, we could adopt recent progress in generative models. Yang Song et al.'s score-based generative model through stochastic differential equations generalized diffusion model as stochastic differential equations. And Elias Freegan point out convolutional generative model is not translation equivariant and solved it via continuation. We release our code and audio samples on GitHub. Please visit our repository. We'd like to thank our friends and teammates Sang-Hoon Woo from MindLab, Jinwoo Kim and Hyunwook Nam from KAIST, Seungwon Park from SNU for valuable discussions. This is references for our presentation, and thank you for listening.